Hi everybody, thank you for joining our next webinar. Today we're going to be discussing the applications of CFD and FEA with SimScale in the construction industry. I think it should be very interesting today because we're going to look at combining two different analysis types within one project. I'm John Wild. I'm the Application Engineering Director here with SimScale, so I'm running the pre- and post-sales engineering teams. I have a decent amount of CFD experience and FEA as well over the years. I've worked at many different companies. And now, enjoying my time here with SimScale. The agenda today, I'm going to talk a little bit about the benefits of using simulation and then give you an introduction to SimScale itself. And then we'll dig into today's topic, and we're going to do that in two different sections. Actually, we're going to look at the FEA and frequency analysis of a building first, and then we're going to look at the CFD using the lattice Boltzmann method on the same building, and we're going to kind of compare and put the results together a little bit. I'll show you in about 20 or 30 minutes. So in a couple of points during that, we'll do a live demonstration as well, and we'll look into looking at live results, and then we'll have a Q&A session at the end. What I would say though is if you have questions along the way, just feel free to type them in, and I'll try and answer them as I go, or we can do that towards the end. Okay, so just to talk about the benefits of simulation, and it really applies in this example that we have today as well. So, I mean, you'll see soon that the main thing for using simulation in this example is really safety. So minimizing failures, definitely reducing costs, and then obviously reducing time investment. So, what we want to do is simulate our designs and make sure that we have the best design that we can and before we go into prototype and manufacture. And a brief introduction as to who we are. We're a cloud-based, browser-based simulation package, so you can run CFD and FEA in a platform that looks very much like what you see on the laptop here, all in browser and all in the cloud. So we're trying to free you as engineers from the kind of low constraints of local high processing power machines and putting it all into the cloud instead. Being running the pre and post sales engineering teams here, on the left hand side the real-time support is one of my most favorite things, I guess, that we do, that we have live help in product. So anytime you're using SimScale, you can pop up a chat and you can start asking us questions, and all of my team and myself included are there a lot of the time to help you as you need it. Like I said as well, we have everything all in one, so you can run different FEA simulations or thermomechanical simulations or CFD, all in the same platform, all in the same interface, and all gets pushed to the cloud. And like I said as well, within the same project today, we're going to look at both FEA, so a frequency response analysis, and a lattice Boltzmann analysis at the same time. You can collaborate really easily, so you just have one simple login that you can share amongst a group, and everybody can kind of see the same dashboard, the same products, and work together on the same analyses. I'd say it's pretty fast and easy. We'll talk a little bit about that today, but some of these analyses took really just a few minutes to run and give us some excellent results. And obviously we're cost efficient. I challenge you to check that out for yourself, and we're also very secure. Okay, so today's topic, we're going to be looking at this building. So it's an 80-meter tall structure, and here you can basically see the open structure of the building. So this is just the internal supporting structure, all of the floors and all of the beams kind of between each. And we're asking two questions. So the first question is, what are the modal frequencies of the structure? So that's like, what are the different frequencies that it will start to resonate? And then the second question is, and here we're going to bring CFD into the mix as well. So how does the flow move around the building, and how does the wind, as it passes the building in a turbulent manner, or could it possibly excite the building in any of those kind of modes that we know? So we're going to do two things. Firstly, we'll look at FEA and the frequency response, and we'll find out what the eigen modes are. And the second thing we'll do is run CFD around the structure and get an idea of the frequency of the turbulence shedding. And then we'll compare the two. So this is just an example of what one of the modes looks like from the frequency response analysis. it's shaded by displacement, so blue is not really moving much, red is moving a lot. It's really exaggerated, but it helps to kind of paint a picture. So later on, if we decide that we do need to start changing the design, this will help us identify what we should change, where and why. So just a little bit about like the basics if you don't know, like what is a natural frequency. So this on the GIF on the left-hand side that's moving is a drum skin. And as you hit it, obviously, it resonates. And everything has resonant frequencies, and everything has different resonant frequencies too. A good example is a guitar string or a violin string. So if you pluck it or bow a violin, you can hear the sound that the string makes as it resonates. And obviously if you change the length, then it'll start to change the note that's played as well. And then if we can understand this vibration, we can then start to dampen it if we need to. I thought this dog was a really good example of how to combat vibration. So he's really kind of damping the vibration with his legs. And here's a really well-known but kind of old example now of why we really need to know the natural frequencies of a structure. So obviously this whole bridge in the end finally collapsed, but it gives you an idea of what can happen, if something is being excited at its modal frequency. Okay, so moving on to the first section, the frequency analysis. I'm going to run in a second into the SimScale interface and just talk you through how to import CAD, then how to set up your simulation, and then we'll look at how to interrogate some of the results that you see as well. And the simulation setup here is pretty simple. Basically, we've got loads of different columns, 30 different floors, and a total of 8 meters in height. And we're simply going to constrain the building at the bottom. So we're going to have fixed supports where it's attached to the ground, as if it were attached to its own foundations. And then we're going to ask SimScale to tell us what the resonant frequencies are of the structure. Okay, so I'm really going to quickly just jump straight into the platform and show you how you would do that. So this is a SimScale interface, which you may or may not be familiar with. On the top here, we can import new geometries. So we go to the plus and upload, and you can import loads of different types of geometry from your own native CAD packages. And then we choose the type of simulation we want to run. So on the left, you can see we have two here. We have a frequency analysis, and then we have our lattice-Boltzmann CFD analysis as well. And if I just go to plus next to simulation, you'll see that there's a whole list of different things that we can do, all in the same project. So there's some different FEA studies, the thermomechanical stuff that I spoke of, and then all of the different CFD analyses as well. So we're going to focus today on the bottom one, which is a frequency analysis first, and then we're going to do an incompressible lattice-Boltzmann method analysis second, and then compare the results side by side. Okay, so once we've brought in our geometry, we mesh it, and all we did here is just press automatic mesh, and then we assign our materials. So basically we assign concrete to the structure. So we actually, by the way, had two different geometries here. One like this, which is hollow, where we're running our FEA analysis, and then one with the cladding on the outside, or windows as well, where we're going to run our CFD study. So this is the FEA model, and we've assigned basically concrete to everything. We have a fixed support at the bottom, so if I just spin it around and take a look, you can see that on the surfaces underneath, these supports are going to be fixed to the ground. And then under simulation control, what I do is say, okay, please tell me, the amount of modes of, that I want to know. So I said, okay, give me 15. We also ran one with 10, just to compare and contrast how quick this ran. And then we can immediately take a look at some results. So under simulation runs here, we've got 10 eigenmodes. And what I can do without having to go into the results is click on the eigen frequency plot. And that will basically give me a plot on screen of all the different frequencies that the structure is going to resonate at. And I can float the mouse over them, and you can see that these are the different frequencies. So later on, if we find that the turbulent flow around the building happens to coincide with any of these frequencies, we have a problem on our hands. So it means that the building will start to shake and will definitely resonate as the flow is passing by it. So we then need to start to think about design changes as well. Once we have some results, we can also quickly jump into them as well, and you can basically see them. So basically, we get a list of all the different eigenmodes that SimScale has predicted for us, and we can choose, if we want to animate any of them, and that will basically help us understand, how this building is going to move. So if I click the three dots here, basically you can see a list of the 10 eigenmodes and the frequencies in seconds that it will respond at. So this one down here at 0.67. If I click the play button, and it will be pretty exaggerated, I think, something like double at least, so it's going to look like an exaggerated motion, but you can see basically how it will respond. And that means if the CFD result happens to coincide with this one, we can say, okay, how does the structure then move, and what can we do to strengthen it in those areas or dampen it in those areas and try to prevent it from moving. Okay, there you go. So it's a pretty random movement, but it's interesting to see. And if the CFD result happens to match this, then we need to think, okay, what is it that we need to come in and start to change? It's often easier, by the way, if we look at it just frame by frame as well. It gives us the kind of true pattern that we can see. So there's basically a wave passing up the building from bottom to top. Okay, so jumping back to the presentation, just to kind of summarize those results. So what we can get, and this took, by the way, 9 minutes to run in SimScale, so it was really fast to give us these results. It basically gives us, obviously, the graph of frequencies that the building is going to respond to. And there's a table on the right, and we'll use it again to compare later on when we have the CFD results. And as I said before, we can float the mouse over the graph and capture any of these points to get the exact frequency number. And just to give you an idea of the kind of different and varied responses that you can get, these are the first 4 modes listed. And you can see it's moving in pretty different ways, right? So on the left and right, it's swaying a little bit. On the left, rather, it's swaying a little bit. On the right, there's really a wave passing, from the top of the building to the bottom. And the third one actually is kind of expanding and contracting, so it's a totally different type of motion, which is important to see, because if we do have some kind of response as the flow passes the building, then we need to know which of these has been excited so that we can then go in and start to make some changes. Okay, so what I plan to do here is similar to before, so kind of explaining what we need to do, and then walking through the setup within SimScale, and then we can start to take a look at some of the results as well. And these are pretty amazing because it's really transient flow and really, really turbulent and complex flow past this actual quite simple structure, but it creates some pretty beautiful images. So we do a couple of things. We bring this part into SimScale as we did before. We choose the incompressible LBM solver, which is probably the best for kind of running these long transient studies. We draw a box around it, which is essentially our wind tunnel. At the inlet, I've assigned a velocity profile. I'll show you how to do that in SimScale in a second, but basically you can import a profile, right? This is an example of one, which is essentially your atmospheric boundary layer. And then on the right-hand side, we have the pressure outlet. And then your walls you can decide. So often we might have slip, which basically means that there's no friction. But if you're running inside a wind tunnel and you want to match the wind tunnel, you might actually want to leave friction on the walls because they do play a part. And then you would start to correlate with the wind tunnel results as well. We're going to run 3 different studies. Often in wind tunnels, you might run 36 different wind directions, so every 10 degrees around a building within a city. You can do that too, and I'll show you in a second how to do the different directions and rotate the CAD around very quickly without having to change anything outside of SimScale. We're actually just going to run 3 directions and compare them again side by side. So we have the first case where the wind's coming from the left, the second at 45, and the third case where it's coming from the bottom. And this gives you an idea of what the results will look like. So this is running from time 0. So basically at the beginning there is no flow at all, and then it's starting to ramp up over time, and you can see the flow looks super turbulent, and it looks really nice. I mean, this is like a lower resolution image just so I could get it into the PowerPoint, but obviously you can get some more high-res stuff from the platform itself. So this is giving us the vortices as they're kind of being shed from the building, and we're going to get the loads and moments of the forces on the buildings too. And then once we have these results, we'll compare them to the frequency response from the FEA analysis, and we'll see if we have any kind of correlation. Okay, so again, I'll jump back into the platform and just show you really how that was set up. So this time when we go to simulation, rather than picking frequency analysis, we would pick the incompressible LBM analysis. And there's, by the way, different types of turbulence models that you might choose. We're using DDS turbulence model, which is pretty good for wind loading and capturing the eddies around the building and also the forces on the walls. The one below is probably a little bit better if we're really capturing, if we want to capture the exact forces. So if you're running a wind tunnel study, this might be a little bit better to basically capture point kind of data on the surfaces of the structure itself. The setup is really, really simple, and it's essentially meshless as well, so there's nothing that you need to do at the beginning. It's basically creating a grid in the background for you, and that is all done really quickly too. The most important thing is basically this external flow domain. So this is essentially your wind tunnel, and you position this around the building. And if you need to run different directions down here where you see rotation angles, you can simply change the direction of rotation. So if you wanted to run every 36 degrees, you could change this to 10, 20, and so on, and get results. Again, side by side and kind of compared on graphs, basically of the results at different rotation angles. So we just use this 3 times to get the 0, the 45, and the 90 degrees. There's only one material. We're not modeling the building, so we basically just have air assigned to our external flow domain. All of the boundary conditions are going to be self-populated for you, and you can customize and change them a little bit if you need to. We did, so basically the velocity inlet by default is just a flow rate, but what we wanted to do is change it to a graph. So here basically you can import a CSV file if you will, so if you want to. So we basically got at different heights, different velocities. So nearly 0 at the ground, and the speed is kind of ramping up as we get higher up into the atmosphere to capture that atmospheric boundary layer. On the opposite end, we have a pressure outlet. So this is an X maximum. So you can see on the bottom right here, on the very far right, we have the maximum X. And then the sides you can change, right? So at the beginning we have slip, but you could change those if you wanted to have no slip. So then you're modeling more of a wind tunnel. Again, under simulation control, with the frequency response analysis, this window looked a bit different because we were choosing how many eigen modes or natural frequency modes to capture. Here we're basically saying, okay, how long in real time do we want to run for? So we ran for 60 seconds. So a minute in real time of the air passing over the full-scale building. The mesh settings you can choose, but basically it's a list kind of from very coarse to very fine. You can customize it if you want to, so you can dig in and refine surfaces and different regions. But for these kind of studies and anything like pedestrian wind comfort too, we find these are pretty suitable. Okay, and then we run it. So we've got the X direction, 45 degrees, and a 90 degrees. And if we basically just dig into one of these results, we set up under the X direction a few different things. The most important thing we want to know before we take a look at what the image looks like are the forces and moments on the building. So under each direction, basically there will be a plot. So we've got forces and moments in the X, and under 45 degrees we have the same. The graph will of course be different, but it's giving us the forces and moments for the 45 degree angle. If we go back to the X direction, which is the one we're looking at right now, Some of the values change a little bit over time and others have a much higher magnitude. What we want to do basically is turn on or off some of those to really kind of hone in on the ones that we're most interested in. So here we're interested in force in the y direction. So that's the lateral forces acting on the building. And that's the black line. So if I turn off all of the others, okay, now we really get to see that there are pretty significant forces on the buildings. You can see them in newtons here. And we can also zoom in right on a small section and then start to get an idea if there's a repeating pattern and then what the frequency and amplitude is as well. Okay, and then if we dig into one of those results, we can start to take a look at what this looks like. So again, this is just a cut plane across the building, and if we press the play button, we can animate it again over time. Maybe we'll look at it from the top. So you can essentially see the flow developing from the beginning until it's fully developed. It never looks totally smooth, and that's great because the flow is transient and we're capturing that transient effect. So you can always see the vortex shedding from the back of the building. And obviously the forces on the building are also constantly changing. Let me just zoom right on the building there. So it never really gets stable. Okay, and then from this point, what we want to do is extract this data. So we have our forces and moment plots. And we can basically jump back into the presentation to get an idea of how these things, or if the frequency response and the CFD response have any kind of correlation with each other. So this is, like I showed you before, the force acting on the building in the y direction, which is laterally. And to give you an idea of what these look like in different directions. So this is like the force in the x direction at the beginning. And we can do the same right in any of the different directions. And the flow looks really, really different depending on the direction that we're looking. And the force response as well will be very, very different too. And I can show you that in a chart in a moment. So there's some huge variations with this particular angle too. You can even see flow quite close to the building, just returning. It's all coming back on itself. And this is at a cut plane roughly half of the height of the building, so at about 40 meters. And you can see them all side by side too, which is a nice thing to do, I think, because it helps us understand, you know, if we have a problem in one direction or all directions, once we start to compare these results. And the same on a vertical cut plane. I thought I'd show these just because they look so beautiful, and it's really amazing to see something so chaotic and transient but also accurate. And you can see the flow almost looks like it's traveling back towards the building, so there's some huge vortices and some negative pressures that are essentially sucking the air back towards the building behind it. Okay, and then we get to the time or the point where we can compare these results side by side, or try and figure out if we have any design problems. So on the left-hand side, basically we have the list of 15 modal frequencies. The frequencies, by the way, are in seconds, and it gives you an idea of the how and when the building will start to vibrate. And on the right-hand side, you can see that we have the force or the frequency of the force acting on the building. So a few in the x direction, a few at the 45-degree direction, and then a few at 90. And some of these do correlate. So we would definitely have a problem in reality in a couple of these directions. So if we were to build this building as it was, and the flow passed it at this velocity, the building would excite two of these natural frequencies, and the building would really start to move and to be forced to move. And really, just to conclude, so there's two modal frequencies that are definitely going to be problematic. And we can identify those obviously by running first our frequency response analysis, and then second our lattice-Boltzmann flow analysis. And now we would need to make some design choices. So we either need to make a change internally to the building, so we could somehow damp the building with a pendulum or some other kind of design, or essentially redesign it. And we know that basically it's responding in the 12th and 15th modes. So what we would do is really dig in and understand how it moves in those modes, and then try to decide, okay, what can we do to combat that? And the other thing we could do is to make some changes externally. So we could make some changes to modify the shape of the building, to hopefully change the way the flow passes around it, and reduce the lateral forces and reduce the kind of hugely and kind of heavy transient effects as the flow passes. Okay, I see one question basically asking me to, I'll do that as I'm talking, go back and take a look at a couple of the eigenmodes to see what they look like. So if we say, I can do this under the 15th one I think I need, right? So we had 12 and 15 I think that were vibrating. If you want to see one of these and see what it looks like, we'll take a look at, say, number 12. And I can also answer the question about meshing in a second too. I'll show you what the mesh looks like on this structure, and it is totally, again, automated, but we'll take a look. So basically, if I choose, say, the 12th eigenmode down here, and what I can do is add an animation, and then start it moving. Okay, so this is going to start to load, and then we can take a look at how it's going to move. And there's also an interesting question, and it is a good one, and it's you make a good point. Why did we model this with concrete only? So yes, you would not do that in reality, of course. We're doing it simply just to show you, how to set this up. But yes, you could set it up much more accurately if you wanted to. All I'm really trying to do is give you an idea of how we can use the frequency response analysis in conjunction with the lattice-Boltzmann method to start to analyze our building. While that's forming, I'll jump to the other one actually and quickly show you what the mesh looks like for this too. Just to answer the other question, basically it's a totally automated TET-dominant mesh, and we didn't do anything other than simply create mesh. And if I zoom in once it's loaded, you can see what it looks like. Okay, it gives you an idea. Hopefully that helps to answer your question. So it's focused, where it needs to be. And it was enough mesh to give us an idea and capture what we wanted to do here. And we can see, by the way, if I jump back to the other study, that the 12th response was again kind of wobbling, but had quite a nice torsion up the building as well as the force kind of propagates. There's a couple of other questions too. So you're interested in the flow separation and propagation into a set of buildings. You could do that too. There's no reason why not. With the same solver, you could simply apply it to an open structure. So we could apply it, for example, to this structure without the cladding on the outside, and you would of course see how the flow moved internally, any vortices created by the vertical columns. That's totally possible as well, and it should pretty much happen by default. So the mesh would capture all of those small features for you. So yeah, we could do that for sure. And yeah, I think you're saying about a series of buildings. We're actually just about to publish the a pedestrian comfort study on an AIJ, which is a Japanese city basically, and I suggest you keep an eye out, and once that's published it'll give you an idea of the kind of huge scale that we can work on with the lattice Boltzmann model. And again, if you had any of those buildings open, the flow would simply pass through them, so all of that would happen pretty nicely and accurately. So we're doing that to publish a validation, a really large-scale validation. And there's a question as well about whether we can do CFD analyses within rooms, or at least demonstrate it. I'd suggest two things. One, we're running another webinar on Thursday exactly on that topic, which you're welcome to join. The second thing is there's a lot on our website. So if you take a look on SimScale.com, there's loads and loads of public HVAC projects to take a look through. There's some of them are mine too. So if you look for J. Wild or John Wild, you'll find some nice studies that I've created as well. Yeah, and I think to answer your question, Ahmed, I think I did answer. So you could have a set of buildings or set of building blocks, really as complicated as you want to make it. The way the lattice Boltzmann solver works is that it can capture a lot of really complicated geometry without much fuss or hassle, and without needing any kind of additional thought as to refining the mesh. So I suggest you simply give it a go. Okay. That's actually answered everyone's questions so far, I think. So unless anything else comes pretty quickly, what I suggest we do is wrap up for now. You're more than welcome to join us. We have a HVAC webinar. It's called HPAC. There's a really huge organization, and they're running a webinar, or we're running a webinar with them on Thursday. And then we have another one coming up in March about how to calculate the pressure drop across a valve using CFD, so much smaller scale than we have here. And of course, you're welcome to join. So thank you for your time today. I hope you enjoyed it. The recording will go on YouTube, and also a link to my deck and the project as well. Thanks very much.